Once again, I welcome on the class of Geotechnical Engineering. So in the last class, I have discussed about the Laplace equation in two dimension, and we have seen the expression of Laplace equation, that is del 2h by del x square plus del 2h by del y square is equal to 0. And the solution of this Laplace equation will give the two set of curve. One set of curve is called a flow line, and other set of curve is called equipotential line. So what is flow line and what is equipotential line? I have already discussed in the previous lecture. And after that, I have discussed the what is the Flownet and what is the properties and uses of this Flownet. So four uses I have discussed, that is the to compute the seepage discharge, to compute the exit gradient, to compute the seepage pressure and uplift pressure. So out of these four, today I will discuss the how to compute the seepage discharge with the help of Flownet, and I will derive the expression of seepage discharge in terms of permeability, change in head, and a number of flow channel, a number of equipotential drop. So let us start the first use of Flownet, that is to compute the seepage discharge. So for the computation of seepage discharge, so firstly I will derive the expression. Let us assume this is our flow line and this is the equipotential line. This is our equipotential line. So let us assume this is our first flow field, this is the third, and this is the second flow field. So this dimension, if I take, firstly I will write this is the flow line, and the perpendicular is line is equipotential line. So this dimension is this is second, this flow field is third, and this flow field is first. So this dimension is A1 and this dimension is B1. Similarly, this dimension is A2 and this dimension is B2. Similarly, this dimension is, let us assume this is A3 and B3, and the flow is along this direction. This is also delta Q. So this is 1, 2, 3 are the flow field, and if I measure the head, so let us assume this is the level of water. Similarly, at this point, so this is the level of water, and the change in is delta H. Similarly, if I measure here, so it will be, so it is also delta H. So this is the flow line, and equipotential line are perpendicular to each other. So we can see this is the equipotential perpendicular to each other, and this is the flow path. This is the flow path. Along the flow path, our flow will be possible. So first, second, and third is the flow field. So what is the properties of flow field? So it will be in the shape of a square in shape, means A1 is equal to B1. So if I write, let delta Q1 comma delta Q2 and delta Q3 be the seepage discharge, and delta H1 comma delta H2 delta H3 be the head loss in the flow field 1, 2 and 3 respectively. So we can write according to Darcy law, delta Q1. So delta Q1 is equal to Ki into, according to Darcy law in terms of discharge, so Q is equal to Kia. So the coefficient of permeability is same. So let us assume coefficient of permeability is K into I. I can be written as delta H1 divided by, so length of the path, so it will be A1. So we can write delta H by A1. So delta H by A1 into area. So B1 into 1. Similarly, delta Q2 can be written as K into delta H2 by A2 into B2 by 1. Similarly, delta Q3 can be written as K into delta H3 divided by A3 into B3 into 1. So here in a different flow field, so delta H1 is equal to delta H2 is equal to delta H3 is equal to delta H, and delta Q1 is equal to delta Q2 is equal to delta Q3 is equal to delta Q. So we can write delta Q is equal to K into here we can write here we can see that, and because this the shape of the flow field is A1 by B1, B1 by A1 is equal to B2 by A2. So here for the here one thing I write, that is for the shape of field flow field is square in shape. So we can write B1 by A1 is equal to B2 by A2 is equal to B3 by A3 is equal to unity, because it is the shape of a square. So we can write here delta Q1 is equal to K delta H1, delta Q is equal to K delta H2, and delta H1 delta H2 delta H3 is the same. So we can write delta Q1 is equal to delta Q2 is equal to delta Q3. Similarly, if I write let, so delta Q can be written as K into delta H. Let us assume this is our equation first. So let capital H be the total head in the, let capital H be the total head in the total equipotential drop ND. So here we can write delta H is equal to H by ND, where ND is the number of equipotential drop. So here I have written let capital H be the total head in the total equipotential drop ND. So delta H is equal to H by ND. So if I put the value of delta H, so the from equation first, so delta Q can be written as delta Q is equal to K into H by ND. Let us assume this is our equation 2. Let NF be the total flow channel. So we can write delta Q is equal to K into H by ND into total flow channel is NF. So delta Q can be written as K into H into NF by ND. So this is the expression of seepage discharge. If the shape of flow field is a square. Otherwise, if I write, if the shape of the flow field is not a square, so we can write delta Q is equal to K into H NF by ND into B by A. If the shape of flow field is not in square shape. So here delta Q is the seepage discharge, K is the coefficient of permeability, H is the change in head or total head, NF is the number of flow channel in the flow net. So NF is the number of flow channel in a flow net, and NF can be written as number of flow line minus 1. Similarly, ND is the number of equipotential drop, or it can also be written as ND is equal to number of equipotential line minus 1. So with the help of this, we can compute the delta Q is equal to K into H into NF by ND, where NF by ND is the shape factor. NF by ND is called shape factor, and it depends on the boundary condition only. So NF by ND is the shape factor, and that depends on the boundary condition only. Here we can see, so NF by ND, the seepage discharge depends on the coefficient of permeability, change in head, and shape factor. So how to compute this NF and ND? Our main focus is to how to read the value of NF and ND. So for a given flow channel or flow net, so let us assume this is our flow net. The first example I am taking, that is this is our flow net. So this is example first. So this is the flow net. So here this is called upstream side, and this is called downstream side. So water flows from higher head to the lower head. So flow will the chances of flow will be occur in this way and in this way. So here the number of flow channel is in a flow net is how much? So 2. So NF is equal to 2. Similarly, number of equipotential drops. So this is first, second, third, fourth, 5, 6, 7. So if I write about the number of equipotential line, so this is 1 and 2. Similarly, if I discuss the potential drop, so it is 1, 2, 3, 4, 5, 6, and 7. So ND is equal to 7. Similarly, if I see the NF and ND value in this channel, so how many flow channels are there? So flow can be from here to here. So this is the first, second, third, and fourth. So NF is equal to 4. Similarly, number of equipotential drops. So this is the first, second, third, fourth, fifth, sixth, 7, and 8. So ND is equal to 8. And the capital H is, what is capital H? So this H1 minus this H2 will be the capital. Let us assume this is the H1, and this distance, this height is H2, and this is called upstream side, and this is called downstream side. So capital H can be written as H1 minus H2. So this is the way to read the value of number of flow channel in a flow net and number of equipotential drop. Similarly, let us take the another example. So this is the another example of Flownet. So here we can see that the flow can be from this way to this way. So 1, 2, 3, 4. So NF is equal to 4. Perpendicular direction, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. ND is equal to 14. Similarly, if I take this example, so if I talk about the capital H, so capital H means change in head is 6.3 because downstream side is uh, sorry, this distance is, and from this distance. So if I and if the number of flow lines, so number of flow lines, flow can be possible from this way and this way. So NF is equal to 3. Similarly, equipotential drop 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So ND is equal to 10. So I hope you have understand how to read the value of number of flow channel and number of equipotential drop. Once again, I am telling this way the flow can be possible, from this way flow can be possible, from this way flow can be possible. So this is the movement of flow. This is also can be the movement of flow, and this is can also be the movement of flow. So NF is equal to 3. Similarly, ND 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So the ND is 10. Similarly, the another example I have taken here, the we can take this is 1, 2, 3. So NF is equal to 3. Similarly, equipotential drop 1, 2, 3, 4, 5, 6, 7, 8, 9. So I think it is the same example. So ND is equal to 10. So once we have read the value of NF and ND, so we can compute the seepage discharge. So let us discuss the first problem. So this problem is asked in GATE 2014. The flow net constructed for a dam is shown in the figure below. Taking coefficient of permeability as 3.8 into 10 power minus 6 meter per second. So the quantity of flow in centimeter cube per second under the dam per meter is. So if I compute the, so we have the seepage discharge is delta Q is equal to K into H into NF by ND. So here coefficient of permeability is given 3.8 into 10 power minus 6 meter per second, and H is the head difference between the upstream and downstream. So we can see that the value of H will be it will be the same level. So H the value of H is equal to 6.3 meter. So we have to read the value of NF and ND. So we can see that the number of flow lines, flow channel. So this is the first, second. If I write first, second, and this is the third flow channels. So this is the third flow channels is 3. So we can write NF is equal to 3. Similarly, potential drop 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So the value of ND is equal to 10. So the seepage discharge can be computed as delta Q is equal to K into H into NF by ND. So the value of K is given 3.8 into 10 to the power minus 6. So 3.8 into 10 to the power minus 6 into H is 6.3 meter. So 6.3 into NF is 3 divided by 10. So if I compute this value of delta Q, so it will be 3.8 into 6.3 into 3 divided by 10. So it is 7.182. 7.182 into 10 to the power minus 6 meter cube per second per meter. So we can we have to find the quantity of flow in centimeter cube per second per meter. So if I convert this value, so delta Q is equal to 7.182 into 10 to the power minus 6 into, if I convert in centimeter, so it will be 10 to the power 6 centimeter cube per second per meter. So the delta Q is equal to 7.182 centimeter cube per second per meter. So this is the quantity of seepage or seepage discharge for this problem. Similarly, the second question, this is the second question, and this question is asked in GATE 2012. So the flow net around a sheet pile wall is as shown in the sketch. The coefficient of permeability is given 0.09 meter per day, and it is written, it is isotropic, means in each and every direction the coefficient of permeability will be same. So the seepage loss in meter cube per day per meter length of the wall of the water is option A 0.33, option B is 0.38, option C is 0.43, and option D is 0.54. So firstly we will see the so this is the flow net is given, and this is flow net. So if I talk about the flow line, so these are the this is the flow line. So this is the flow line, and perpendicular to this is equipotential line. So we have to once again find, so firstly the delta Q can be written as K into H into NF by ND. So here the head, capital H is the change in head. So this is the upstream side and this is the downstream side. So capital H can be computed as 10 minus 1.5. So this is the change in head. So this value will be capital H. So capital H can be written as capital H is equal to H2 minus H1. H2 is the head in the upstream side. So it will be, this is, let us assume this is H2. So this is H2 and this is H1. So it will be 10 minus 1.5, 10 minus 1.5, so it will be 8.5 meter. Similarly, if I see the value of NF, so how many number of flow channels in a flow net? So this is first, second, third, and fourth. So the value of NF is equal to 4. Similarly, number of equipotential drop, if I read, so number of equipotential drop, first, second, third, fourth, fifth, sixth, 7, and 8. So number of equipotential drop is 8. So number of equipotential drop is 8. So the seepage loss or seepage discharge can be computed as K into H into NF by ND. So the coefficient of permeability is given. It is coefficient of permeability is 0.09. So if I write 0.09 into head is 8.5 into 4 by 8. So it will be 0.09 into 8.5 into, so it is 0.38. So this is 0.38 meter cube per day per meter. So if I see the option, so 0.38, so B option is correct. So this is the option correct. So just we have to read the value of, if you know the how to read the value of, or how to take the value of NF and ND, so it is nothing, we can easily compute the seepage discharge just by putting the value of NF, ND, and K and H. We can compute the value of seepage discharge. So this seepage discharge is the function of coefficient of coefficient of permeability change in head or total head, and the third one is shape factor, that is NF by ND. So this shape factor NF by ND is the only function of if I write this shape factor NF by ND is the only function of boundary condition. And if I talk about the salient points, about the important points about flow net. So the first point is shape factor, that is ratio of number of flow channels by number of equipotential drop is the function of boundary condition only. Second one, flow net will not change if the coefficient of permeability changes. So flow net will not change if the coefficient of permeability changes. Similarly, flow net will not change if there is changes in the head loss. So these are the few points about the flow nets. Shape factor is the only function of boundary condition, and flow net will not change if the coefficient of permeability changes. Similarly, flow net will not changes if there is a change. Flow net will not change if there is a changes in the head loss. So dear student, today I have discussed about the how to compute the seepage discharge, and the expression was Q is equal to KH NF by ND, where K is the coefficient of permeability and capital H is the change in head, and NF is the number of flow channels, and ND is the number of equipotential drop. And after that I have solved the few problems based on the how to compute the seepage discharge if a flow net is given. So the main thing is we have to how to read the value of NF and ND, and after that it will be very easy to compute the seepage discharge. So in the next class I will discuss the how to compute the exit gradient, and after that seepage pressure and uplift pressure with the help of this flow net. So take care of your health and happy learning.